I remind you what we have done. We discussed the OSI and TCP/IP, and we said we have these layers, right? So layer number one is what? The first layer, the most important, if you think about, which has to do with engineering, is the physical layer. Thank you so much, Sarah. The physical layer. The physical layer is where all the physics happen, right? The signals, the data, and all these things. We discussed them last chapter. So we discussed how do you set this data as a signal, and the science behind it. So once I finish the physical layer, what's the next layer? What's the next layer? The data link. Yes. So bonus point for Sarah. Bonus point for Sarah because she's very active today. So the data link layer. Okay. So you have the physical layer, then you have the data link layer. Today is all about that. So we're going to talk about the data link layer, the MAC layer, which is part of the data link. So if you look at the data link layer, we have the LLC, we call it, the link control. That's a sub layer. So my data link layer is divided into two sub layers. The medium access control, the MAC. This is called the MAC, which is the most important, to be honest. The MAC. And we have the LLC, which is the link control. Okay? So mostly the MAC is where all the magic happens, the medium access control. So we'll be discussing the medium access control, the different kinds of medium access control that we have. So the main job, if you go back to the jobs, the main job of the data link layer is error correction, error detection. The physical layer deals with bits. The data link layer deals with what? What does the data link layer deal with? What's the unit? Frames. Excellent. So you have bits. Now we're talking about frames. So we bundle these bits together, and we could do some mathematical calculation on them, like something called Hamming code, something called checksum, where I do calculation. I could figure out, this message or this frame got corrupted because I have a formula that says if I sum all the bits, it should be 5, but what I got is 4. So therefore, maybe something happened to it. So all these magic are done in the data link layer, as well as medium access control. The data link layer is the one that decides on who gets the medium. I need to control this because otherwise it's going to be a big mess, because we're going to have a whole bunch of collisions where packets and messages will hit each other. It's like traffic control. Imagine on the highway of Sheikh Zayed, you don't have police, right? You don't have somebody that controls the traffic. You don't have stoplights. What will happen? What will happen if you don't have traffic control? What will happen? It will be fun, yes. But what will happen? You're going to have traffic jam. What else? You're going to have chaos, collisions, and so on. So obviously somebody has to control who gets access to the media. Or you know what? Let's go back to give another example, an easier example. If I allow all of you to unmute yourself and talk, what will happen? Again, if all of us talk now, unmute and talk, it's going to be chaos, right? Complete chaos. So because you need somebody to control it, say you, Sufyan, what do you think? Sarah, what do you think? Somebody has to control. So think about me as the MAC, where I'm kind of deciding who goes next, and kind of make sure that the class moves on with control as much as we can. We could take turns, that's a solution, but it's not efficient because we waste time. So we will talk about the technologies behind this, okay? So the key issue when it comes to MAC is who gets the channel, who gets access, and medium access control is the one that allows us. So you could have point-to-point, you could have broadcasting. Typically, medium access is where we have broadcasts. So if I'm broadcasting something, we need to make sure that we have control. So let me give you an example. I mean, just thinking about it now. So radio channels, they broadcast, right? Like radio channel, they broadcast. How do you make sure that their voices don't overlap? There's no collision. How do you make sure? How do we do that for radio? In your radio, how do you make sure? Different frequencies. Yes, Rida, good job. So we do something called FDMA, which is frequency division multiple access. So we divide them into frequency bands, and we say, oh, you could all talk at the same time, these radio channels. However, we will control you by using frequency. If I give you time, that would be time division multiple access. So that's called time slots. So you can see there are many ways to do it. So let's see how does the medium access control work? So again, looking at LANs as a good example, these are the common protocols. So you have the random access, the controlled access. Somebody's controlling. So you go next, you go next, you go next. That's controlled. And you have the channelization protocols, which we talked about now. FDMA is frequency division multiple access. TDMA is time division multiple access. And CDMA is code division multiple access. So these are called channelization. That's one way to do it. When you're talking about local area networks like Wi-Fi, very good example, which uses CSMA, carrier sense multiple access. So these are random access, meaning we don't have somebody controlling. It's more randomly. I need access. I need to send. I want it now. How does that work? That's what we call random access protocols. Okay, so you have three major categories. The least common is the controlled. That's least common, not too popular. Some of these are obsolete even. For example, token passing is obsolete. It's not used anymore where you have a token. It's like you have a token, right? You have a coupon or you have a voucher. The one that has the voucher can talk. If you don't have the voucher, you cannot talk. That's called token passing. We pass the token, and if you want to talk, you need to have the token. You see how kind of the simplicity behind it, okay? The random access is different. I wanted the channel, I need to use it. So Aloha is what started the whole thing. I'll talk about it now. So what does Aloha stand for? What language is this? Aloha is what language? Hawaiian, yes, Hawaiian indeed. You know why? Why we called it Aloha? Anybody, a wild guess? Why did we call it Aloha? The first protocol actually? Any ideas? Wild guess? Yeah, I know, but why Aloha? Yes, Muhammad, well done. Okay, I don't know how you know that. Maybe you read the lecture, but yes, bonus point for Muhammad. So yes, indeed, this is how it started. It started in Hawaii. Okay, so why? Because Hawaii has multiple islands.
Professor?
Yes, tell me.
Who's Hamad?
Sorry?
Who's Hamad? The guy who got the bonus point. I don't see him.
I don't know, Muhammad, I think his name. You could see the chat, my friend.
Oh, it's Muhammad.
Okay, thank you. Okay, so you could see the chat and decide. It's fine. Let's not waste time on this. So random access, as I said, we have multiple protocols. Typically, it's contention. Again, contention. What does contention mean in English? What does contention mean in English? What does contention mean in English? Competition. Yes, thank you, Sufyan. So yes, meaning I'm competing. Contention, I'm contending. So contending meaning we're competing to see who's going to get the channel next. So you have multiple protocols. Again, these are the ones. Let's talk about them one by one. So yes, Aloha is a series of protocols. We have two famous ones that started, the pure Aloha and the slotted Aloha. They started in the 70s. Again, University of Hawaii, the whole idea was they wanted to connect the islands in Hawaii, and they're so far from each other. You talk about islands, small islands. They said we need a way to kind of broadcast, to connect them. Obviously, connect them like radio and so on. So ideally, the concept behind it started, and they called it Aloha because this is how it all started. How does it work? It's kind of one of the dumbest algorithms ever. So simple. It says, the first protocol is called pure Aloha. How does it work? Simple. You want to send anytime you want. And if your packet collides, or your frame, because we're talking about data link layer here, if your frame collides with another frame, you resend. As simple as that, you see? So we could try it. You know what? Let's try it now. So please, somebody help me out with this. Maybe I need 5 or 6 of us. Can you do that? 5 or 6? Unmute yourself. About 5 or 6 of you. Please unmute yourself.
Okay, I'm ready.
Yes, somebody else. I need 5 or 6 so that we can understand. Yeah, please, more. I want it to be chaos. Come on. More, please unmute yourself. Yeah, let's have a party.
Okay.
Oh, yeah, perfect. Yeah.
Oh, hello, my name is Afras.
Let's start talking.
Cisco. Yeah, let's go. Yeah.
Okay. Let's stop now.
Yeah, all right.
Thank you. Okay, thank you guys. Thank you.
The
Thank you.
sky and sea.
Thank you. Thank you. YMCA. Thank you, YMCA. Mute yourself. Mute. Mute. Thank you so much. That was fun. You see, that was complete chaos for many reasons. Obviously, because we talked anytime we wanted. Yes. Obviously, in the real protocol, it was more when we have a collision. We know that we have a collision because we could figure it out. It bursts back to me. The channel knows, and you resend it. You could see, for example, here. Again, station 1 sends here. That's fine. And you could see here, this is where the collision happens. You could see. And you hear there is a collision. So if I have a message, let's say 100 bits, right? 100 bits. And I usually when you send, just to explain, you're not sending the 100 bits at the same time, right? You send them how? How do you send them usually? We know it by now. We already did a lecture on this. How do you send them? Yeah? How do you send them? The 100 bits, how do you send them? How do you send the 100 bit by bit? Thank you so much, Sarah. Thank you, Sarah. You are in this class. Thank you so much. You're always active. You always answer the perfect answers. Yes, bit by bit. So I don't send 100 bits at the same time. Obviously, that doesn't make sense in any communication system. So I'm sending them bit by bit. Yes, it's 100 bits, but I send them bit by bit. That's what you need to understand. So I might send 99 bits and everybody's happy. And when I'm sending my 100th bit, what might happen? My 100th bit, what might happen? No, not lost. What might happen to my 100th bit? Look at the picture. What might happen to the last piece of it? Collision. My last bit would collide to a new guy that started sending. So what would I do then? What would I do?
Reset
Resend what?
the same message. The bits.
The whole 100 bits. Not only the last bit, the whole 100 bits, because this is a frame. Losing one bit of it, I would lose everything. You know, this is the whole concept. Obviously, if it's bit by bit, I cannot resend a bit on its own. Would not make sense. The overhead will be humongous. Imagine every time I lose a 1 megabit, 1 million bits, I send only 1 bit again. That would not make sense. So that's the reason. So this is not efficient, obviously. Again, you transmit whenever you want. You actually detect collisions. How do you detect collisions? Just for you to understand. If it is a cable, if it's a bus, I'm a sender. Typically, I know the signal that I'm sent. If there is a collision, suppose it has a voltage of 2, just for you to understand, you would see that if it collides, it's going to bounce back to me. And I would know, this is not what I sent. This is not the same signal that I sent. Therefore, I know there is a collision. So collisions could be detected by something called carrier sense. For now, simple, I send. If a collision happens, I resend. As simple as that. That's what we call the pure aloha. Okay? The pure aloha. So, and usually we know if a collision happened based on the checksum and many other things. Formula-wise, again, usually in my other courses, I will derive this for you. I will derive it. So you can see it's an exponential function, inverse exponential actually. So the formula is simple. The throughput, meaning if I'm sending 1 billion bits, throughput is basically how many you will make it. That's what throughput is, usually the efficiency. So you could see in this case, the formula is GE to the power minus 2G. Again, E is exponential. E is exponent, is exponential, which is in your calculator, E, okay? Which is a constant. Now, the only variable here is G. G is how many attempts per packet time. How many times are you trying to send? That's what we call G. Usually it's given. It will be given to you. So to find the throughput, you can find it. Very simple. Multiply G times E, which is a constant, to the power minus 2G. It takes you 2 seconds in a calculator. Now, this is not what's very important to me. What's very important is if I derive this, you know what the derivative is, right? If I have a function, I can know when it is maximum, when it is minimum. We derive it and make it equal to 0. if you do that, I'm not going to do it for you now. It's very simple. It's basic calculus. Long story short, if you derive it and find when is it maximum, the maximum throughput will be 0.184. Look at that, 0.184. What is 0.184? What is the percent? 0.184 is what percent? 18%. Thank you so much. So basically, the efficiency or the throughput of pure Aloha is 18%. That's super bad, right? That's bad. What does it mean in simple English? What does it mean in simple English? It means as simple as if you are sending 100 times, you would succeed 18 times only. That's what it means in pure English for you to understand. The throughput is 18.4%. Does that make sense? And it makes sense, right? Because of the way it's designed. It's a stupid algorithm. It says, when you want to send, ya khayyi. Send, and if you have a collision, just resend. You know, wait and resend again. And inshallah, your message will get there. Okay? That's how it works. So obviously, inshallah, in this case, it's 18%. Are we good? Are we good with pure Aloha?
Good, sir.
Okay, perfect. So let's move on. So they came and said, obviously, we can do better. You know, this is, again, the first. That was in the 1970s. So this was the first, how it all started. And now you see how Wi-Fi works based on it. Yes, it was the mother. Pure Aloha was the mother of all MAC protocols to follow, okay, in this context. So they came and said, we should do a better job. We can do a better job. We should not allow the station anytime they want to send. Why don't we divide it into time slots? So we're going to make it a little bit better and say, you cannot send anytime you want. For example, you can only send at the beginning of a time slot. For example, 8 a.m., 9 a.m., 10 a.m. If you want to send, you cannot send at 8:30. You can only send at the beginning at either 8 or 9 or 10 or 11, for example. Again, obviously, this is not how it is, but for you to kind of correlate with it. Does that make sense? What do you think? That would decrease the collisions or increase the collision? Do you think that will increase my throughput or decrease my throughput? It will increase my throughput or decrease my throughput. If I kind of say, you know what, you can only send at the beginning of the time slot. Of course, it's going to be better because now my packet cannot collide with yours all the time. It only will collide when it will only collide at the beginning. It will only collide here if we are set, because we can only send at the beginning. So yes, the throughput will be increased, and this is what they call the slotted Aloha. The slotted Aloha. So I divide it into slots. Same thing like Aloha, pure Aloha. The only difference now is I'm sending at the beginning only. I can only send at the beginning. So yes, we still have collisions. We still have collision because when can we collide now? We can only collide if, of course, same time, but if send at the beginning. So we can only collide at the beginning of the time slot. Before it was also at the same time if we send, but anytime. You know, it could collide halfway, beginning, end. Now, no, I can only collide if it's at the beginning of the time slot. So therefore, as you said, the throughput would be better. What do you think the throughput would be? If that was 18%, what do you think the throughput would be now? Just rough, wild guess. Wild guess? Around 40. Actually, it's exactly double. The maximum throughput, that's the maximum throughput, is exactly double. So if you could see now, again, the picture, I could only send at the beginning. You can see I could only send here. Yes, these two will collide. These two will collide, but only at the beginning, you can see. But if I send at the beginning and I don't collide with anybody, I'm fine because my message will get there. You can see? So this is kind of clever. It made it better. To be more specific, it doubled it. You remember? There it was 18%. Now it's 36%. You see? So the formula now is not GE to the power minus 2G, it's GE to the power minus G. Okay? So basically, we doubled the throughput. We doubled the throughput. Okay? There it was 18.4, now it's 36.8. Which, again, cool. Not bad, it's not amazing, but my maximum throughput is doubled, and this is when G equal to 1. How did we get this, by the way, just for you to understand? We derived this. If you know basic calculus, you guys know what derivative is? From high school, from pre-calculus? Yeah. You derive this and make it equal to 0. As simple as that. You could do it now and you make it equal to 0. You can easily find the value of G. And again, obviously, G equal to 1. If G equal to 1, plug it here. If you put G equal to 1, what would it be? 1 times e to the power minus 1, right?
Yeah.
Which is basically 1 over
E.
E. That's it. If you divide in your calculator 1 over E, my friend, you should get 0.368. Okay, because E is about 2.7, right? So you get 0.368. You see, I love this. I love this, how we take networking and kind of play with the numbers and understand how these came about and how we're going to talk about Wi-Fi in a second. Okay, which you use on a daily basis. Are we good? Exciting, yeah? Am I the only one excited here? And Sarah for sure. And Fatima.
No, even I'm excited. I'm not saying anything.
Yeah. Sarah, I want to hear your voice. Thank you. Excellent. Good. So let's move on. Okay. So if you look at the picture, if you like a little bit math, this is the mathematics behind it. You could see this is an exponential function. You could see this is the slotted aloha. You could see the throughput is maximum here. This is where it's maximum, and this is where it's maximum. When it's G equals 0.5, this is maximum G equals 1. And the value of it, you can see 0.38 here. 0.38 is the maximum, and the maximum for this guy is about 0.18. So you could plot it. If you plot it, you could see how it looks like. You could. Let me see if I could do that. That would be fun. Let me just do this real quick. Let me just go Wolfram Alpha. Okay, you guys know what Wolfram Alpha is, right? Semantic web. If I've taught you another subject, maybe I've told you this. So plot y g e to the power minus g. Okay, see if it's gonna get that. Okay, so the x. Okay. So you could see this is x e to the power minus x again. It's nice. I mean, you could draw these pictures, and if I put e to the power minus 2x here, you could see it. You could put them next to each other to see on top of each other, and x e to the power minus x. Okay. Okay, you can see I plotted two graphs. You could see how one is faster than the other. So the red one is xe minus x, and you can see xe minus 2x. You can see obviously xe minus x is faster, therefore the better throughput. So this is again what we have here. Ge minus g is xe minus x, and this is xe minus 2x. Very nice. I mean, I like how we kind of connect the dots. Okay. You can never get rid of math, Muhammad. Math is life. Math is life. If you get rid of math, you get rid of your life. Okay? I'm telling you from now. And again, obviously, never go to computer science if you're going to get rid of math. Go do marketing or English literature if you're going to get rid of math. Okay? Okay, Muhammad? So let's move on. So again, we talked about pure aloha. We talked about slotted aloha. Let's go ahead and kind of go one step further, which we call the carrier sense multiple access protocols. Now it gets interesting. They come and say, 1 second, Aloha and slotted Aloha, good start, but they're not smart. They're very dumb algorithms. How can you make them smarter? What do you think we do? How do you make them smarter? What was the problem with these two guys? The Aloha protocols had a major issue. Is what? Who could tell me? Of course, we always have collision. That's inevitable. But they did something wrong. They let you send, yeah? Whenever you want, right, Sarah? I'll finish your sentence. We're finishing each other's sentences. They send you, they let you send whenever you want, right? So now, what should we do? Before you send, I should make you do what? You can do request and send, not bad. I like the way you're thinking, but we should do what? We should, before I send, what should I do? It's like, again, let's talk again. You know, let's talk. Please unmute yourself. Let's do the activity one more time. Yalla. I need 4 of you. Yalla, chaos team. Chaos team, let's do the YMCA song.
Yes, sir.
Chaos.
Hello.
Yes, how are you guys? Yes, love it. More chaos. Come on.
Can't sit with
Okay, no, serious. Let's do a deal, guys. Let's do it again. But if somebody, before you talk, you need to listen. If somebody's talking, you need to respect. You cannot talk. As soon as somebody finishes, you can start talking. Can we do that again, please? Don't put any music anymore. Don't talk. Quiet. Just say hello and join me, please.
Hello.
Yes.
Hello.
And be quiet. Yes. And be quiet. Be quiet. Yes. About 5 of us, 6 of us. Yes. Be quiet. Now.
Hello.
Okay. So all of us quiet. Let's wait. If somebody's talking like me, you respect because you're listening. You don't say anything. Don't say anything because I'm talking.
Hello.
Huh? You talk. Perfect. We respect it.
How are you?
Good.
Good morning.
Aha. Perfect. This time 2 of you talked at the same time. Yes.
Yeah.
See, I was waiting
Yes.
for 2 of you to collide. So you can see now it's way better, right? It's way more efficient, don't you think?
Yes.
What was the trick? Is we listened. We listened to the medium. And if somebody's talking, we don't send. And if nobody's talking, we send. But there is a probability of collision still, like what happened now. So that was a good exercise. Thank you so much. Well done. Thank you for those who are always taking part in these activities. This is fun. You would always remember this, trust me. So back to the question. So the uniqueness of this is carrier sense multiple access. The carrier sense, this thing is called carrier sense, is what we just did now, is basically listen before you talk. Listen before you send. Listen. And again, this will make our utilization way better. So that's what carrier sense multiple access is all about. Listen and send at first glance. So you have different versions. So carrier sense is listen, and we can either be persistent, meaning as soon as it's available, I'm going to send. That's what we call one persistent. You could be non-persistent, meaning I listen. If nobody's sending, I don't send. I just wait, and then I send. We call this non-persistent. And you could be P-persistent, which means same thing. I listen. Nobody sent. I will send with the probability of P. Suppose P equals 0.5. I will kind of toss a coin, 50-50 chance I will send. I will not always send. So one persistent, I will always send if nobody else is sending. So these are the ones. If you have the non-persistent, it's less greedy. I wait a random time before I send. And you have the P-persistent. I wait. I would send with the probability of P. Okay? So if P was 0.5, I would send 50% of the time. If P was 0.2, I would send 20% of the time. So I have a probability that will define how persistent I am. Persistent meaning how much do I really want the channel. Okay, guys, very nice. I love it. So, any question about the carrier sense multiple access?
No, Professor.
Very nice. And again, this is very important because this is the foundation of Wi-Fi. This is the foundation of Ethernet. Ethernet was based on carrier sense multiple access with collision detection. So that's what we call CSMA CD. CD is collision detection, meaning I could detect a collision. So if there is a collision, I know there's a collision, I do something about it. Okay, I'll be talking about it in a second. So what else do we have? We said we have others like FDMA, TDMA, and CDMA. These are different. These don't say send when you want. We say, you know what? I don't trust you. I do not trust you. I'm gonna give you a slot. I could either give you a frequency slot or a time slot or a code, which I will kind of multiply by the data that you have and get a big message that I could decrypt. It's like encryption and decryption. So FDMA stands for frequency division multiple access. So I'm dividing my frequency into frequency slots. As we said, very similar to what? What's a good example of this where I divide it to frequency? What's a good example? We already said it today.
So can you repeat? Yeah.
No, it is radio. Yes. The question I'm saying, what's a good example of this? The good example is radio, where I divide every radio. You know, version radio is radio.
FM radio?
Sorry?
Is it FM radio?
FM,
Different version.
Any kind of radio. Any kind of radio. TV. TV doesn't have to be radio. TV. Every channel has. Every channel has what on TV? Different frequency. Thank you so much, Sarah. Thank you. Different frequency. So yes, 100%. So the idea is simple. Frequency division multiple access to guarantee that there is no collision. I give everybody a frequency. So that's good. But what's the bad thing about it? Obviously, we're gonna run out of
Frequencies.
Frequencies. Thank you so much. So we cannot keep on giving frequencies. At one point, we're like, khalas, we don't have any. So obviously, this is not a scalable solution. It's still a solution. So the other choice will be TDMA. TDMA is time division multiple access. When cellular phone started, it was very similar to TDMA. It uses TDMA, which means I divide into time slots. I don't allow two people to be using the same time slot. So that's the idea. So again, here we kind of minimize collision. Obviously, it's not a good thing because time will be, that will cause delays and so on. Finally, the last one is CDMA, which is code division multiple access. Again, the logic in it is simple. I divide my data. I give every channel a code. And if you're sending data, I multiply by your code like this, as you could see. So 4 people could be sending at the same time. When you get the message, you can decode it backwards. It's like encryption and decryption. So the message is a combination. I could easily know if you give me this, I could know what was D1, what was D2, what was D3, what was D4, based on C1, C2, and C3, and C4. So that's what we call CDMA. It's a bit complicated, of course. I'm not going to talk about it now, but know that it exists. And basically, that was one of the earliest technologies used for cellular phones, which is CDMA. Okay? So it's a combination of codes associated with each sender, which every person sending on over the channel. Okay, that's what we refer to as CDMA. Very good. So when we look at going back to CSMA, we look at the different technologies out there. The famous one that pops to our mind is the IEEE standards. IEEE came up with many technologies, many standards. Again, it stands for Institute of Electrical and Electronics Engineer. It's a famous institute, you know, I'm a member of it, you know, and you have also ACM, which is the Association of Computer Machinery. It's for computer scientists. So these are big names, you know, these are the people who are putting a lot of the standards out there, especially the IEEE. So the IEEE back in the 80s started and came up with many different protocols out there. And they worked with the physical layer, they work with the data link layer, many different standards. One of the most famous is what we call the Ethernet, which is basically IEEE 802 point, anybody knows? 802.3. Yes, Rida.
Three.
Well done.
I said 3.
Okay, 802.3 is what we call the Ethernet. What about Wi-Fi? Is IEEE Wi-Fi?
2.
No, 802.2, what? 802.11, yes.
Oh, 11.
802.11, that's Wi-Fi. So these are all, as you could see, 802. These are all MAC protocols. They're medium access control protocol based on CSMA, which is carrier sense multiple access. As you could see, the Ethernet starts at 10 megabit per second. Now we have gigabit Ethernet. You have even 10 gigabit Ethernet. You can even know what Ethernet you're using. You know what? Let me check my Ethernet real quick. Let me check my Ethernet. Let me check this. I'm going to check my Ethernet. You can do the same, by the way. You can see my desktop, right? So if I go to
Yes, we can see it.
network and internet settings, if you go to your network settings, you know, if you go and say show connection properties, oh, this is my Wi-Fi, okay? If you go to Ethernet, you see Ethernet? You can see this, right?
Yes, Professor.
Okay, if you go to Ethernet, okay, you click on Ethernet, it says not connected, obviously because I'm using Wi-Fi. It says, if you go to show adapter options, you can even see my Ethernet. I have 2 Ethernets. I think one is a virtual one. Yeah, this is virtual. This one, let's see the properties of this. Okay, if you go to properties, you could see this is it. It's Intel Ethernet LM. Okay, I think this is a gigabit Ethernet. Let me copy this. Let's Google this. Let's Google my Ethernet. I think this is a gigabit. I think I have a gigabit Ethernet. Let's double check. It's a low gigabit Ethernet. So if I go here, let me Google this real quick to see the model. So yes, this is the model. Yes, as I expected. You see, product collection is a gigabit Ethernet, up to 2.5 gigabits. So I have up to 2.5. This is my Ethernet. You can check yours real quick, you know. It's a low power. LP stands for low power, 1 gigabit Ethernet at the layer. Okay? Interesting. You see? Again, very basic. Let me go back to the lecture. You could check out yours as well. So yes, we have different versions of the Ethernet. Again, how does the Ethernet work? Real quick. In terms of what kind of protocol it uses. Okay? Did any one of you check yours? Anybody check theirs? What kind of Ethernet do you have?
No, Professor.
Yeah, I'm asking who did, who checked.
Mine goes till 5 gigahertz.
Not gigahertz. It has to be gigabits. Okay. Okay. 1211. Okay. 2.5. Yeah. I think most recent Ethernet adapters go to that. Yes. Thank you guys for those who checked as well. Okay. So good. Unless you're using like an older version, but most recent computers will be in that range. I was kind of wondering if anybody went to 10 gigabit Ethernet, you know, that would be super fast. Okay. So anyway, so back to Ethernet, how does it work? It started as Aloha, then they added carrier sense to it, which means I could sense the medium. It started at 3 megabit per second. They called it Ethernet because scientists thought Ethernet or ether is what made, you know, the world. You know, I think in Avengers they use ether. You know, the guy with the gloves and the stones, the Infinity Stones. They talked about ether, right? Do you remember? Yeah. So this is really the Avengers, the movie. I think the Infinity, again, ether is what made the world and stuff like that. So that was kind of something. I think Thanos, if I'm not mistaken. Anyway, so the idea people thought before ether is a substance that kind of made up what we're doing and stuff like that. Okay. Anyways, so that's why they called it Ethernet. That's why they called it Ethernet. You know, Ethernet. It allows waves to propagate. Therefore, they call it ether. So yes, it started as 3 megabit per second, and then it went to 10 mega, then went to giga. So how does it work? The logic is very simple, and pay attention. This is not going to be, it's going to be interesting now. You have Ethernet. It uses carrier sense multiple access with collision detection. So what is carrier sense multiple access? Who could define it for me really quick? Just unmute yourself. Let me give you a bonus point. I want to hear your voice. Don't type. Don't type. Unmute and explain to me. I'll give you a bonus.
Is it like when like it listens to the medium before it sends the packet?
Yeah. And then?
And then do I explain like CD?
Yeah.
I'm not sure. I think I read about it. Is CD like where it sends?
No, sorry. You didn't read about it. I just explained it. I already taught you this 20 minutes ago.
Maybe it's just like the example we did.
Let me finish. Let me finish. Let me finish, please. Yeah. What I told you before, like 10 minutes ago, I explained how it works. Yeah. Are you there?
Sorry, I don't understand.
Okay, that's fine. That's fine. You tried. Thank you so much. Again, I said it. So you sent.
Can I try?
Sorry. Yeah.
Is it like it gives each one like so each one goes by turn, like each one has their own job?
No, it's not by turn. Carrier sense, I could send anytime I want, but the only difference is I sense the medium first, as she said. I listen to the medium. If nobody else is sending, I have 3 choices, basically. I could wait and then send, or I could send immediately. We call this one persistent, or non-persistent, I wait, or P persistent, I wait with the probability to send. Now, collision detection, as I said, is I said, if a collision happens, I can detect it because I am in transmitting mode. So I could notice that the voltage will burst back to me. I explained it like 10 or 20 minutes ago. Because I have this ability of collision detection, I have like a machine that's here. It's kind of listening to the medium. You are sending. You're still sending. It's still listening. If it hears, it's like somebody putting their ears on the cable and say, oh, shh, oh my God, there is a collision. There is a collision. Resend. That's how it works. This is the whole collision detection. I kind of detect the voltage burst back to me because if 2 signals hit each other, it's going to kind of backtrack to you, the sender. You're going to get, it's like, like a ripple effect. Think about it as a ripple effect. So if I hit the ball on the wall, the ball will come back to me. If there is no wall, what will happen to the ball? If there is no wall, what will happen?
It will keep going. It will not
It will
come
keep
back.
going. Thank you so much. If there is a wall, hence there is a collision, the ball will hit and come back to me. I would hear it because I have a collision detection capability. Okay, I hope I explained it well. Is it clear how the CSMA CD works? I listen, I send, collision happens, I know it happened, comes back to me, I resend it. That's as simple as it gets. Now, there is a trick. There is a trick. The trick is for you to send, again, obviously, the idea is I could be in 3 states. I could be either in transmitting mode, receiving mode, or cycling mode. So I'm either transmitting, I'm sending, receiving, I'm waiting for somebody to send me, or cycling between them. Okay? So this adapter can be either in transmitting mode or in receiving mode or cycling between both. And the time to cycle is basically 9.6 microseconds. You can see it's very small. To cycle from one to another, it takes you 9.6 microseconds. So this is the time that IEEE 802.3 specified. So before you can submit, before you transmit, you have to wait 9.6 microseconds just because I want to allow somebody to cycle from transmitting mode to receiving mode. So if I want to send, I don't send immediately. IEEE 802.3 said, you know what? Wait 9.6 microseconds. Why did they say that? Why should we wait 9.6 microseconds before I send? To allow who? To do what? Why do I wait before I send, according to IEEE? Allow who?
Third party.
Allow who? If I'm sending to you, why should I wait 9.6 microseconds? To allow you, the receiver, to cycle from transmitting mode to receiving mode. Does that make sense? Because if you were still in transmitting mode and I send you, you would lose the packet. Does that make sense? And the time it takes to cycle is 9.6 microseconds. That's the first thing to remember. I hope you got this. So let's move on. The second thing to remember is, very important, to detect the collision. Remember CSMA CD. I need to be able to detect the collision. For me to detect the collision, I have to still be in transmitting state. I love this. This was the key to something we'll be discussing in a second. So I can either be in transmitting mode or receiving mode. Very simple. If I am in transmitting mode, I am able to detect the collision. But if I am in receiving mode, I will not know that a collision happened. Therefore, for me to detect a collision, I have to be still transmitting. And you have to remember, if I'm transmitting, this is me, I'm sending, right? I'm sending a frame, suppose. What is the time, a frame of size S? What is the time it takes me to transmit the whole thing? What did we call it? What did we call it? Do you remember? In network performance, one of the lectures. The time for me to send this whole frame, bit by bit. What do we call? What kind of delay? What is it called? Is it called queuing delay? Is it called propagation delay? What is it called? Transmission delay. Thank you, Basim. I think Basim was the first one to say it. Bonus point. So the transmission delay. The time for me to transmit this whole thing is called the transmission delay. So we want to guarantee so that you will be able to know that the message arrived successfully without a collision happening. We want to guarantee that the time it takes you to send this, meaning you're still transmitting, because you have to be in transmitting mode for you to detect the collision. The time it takes you to transmit it should be at least the round trip time, you see? Because if I'm here, I'm A, and I'm B here, and you're B, and I'm sending you something, right? And then 20, 20, 20, 20, 20 here. What if a collision happens here? I should be able, this should come back to me, right? For me to know that there is a collision. And for me to know that there is a collision, what state should I be in? Who could tell me? What state should I be in for me to know, to detect the collision? What state should I be in? Transmitting mode. So I have to still be transmitting. I have to still be transmitting because if I cycled and I went to receiving mode, I will not be able to know that a collision happened and the whole thing will be bogus. So we want to guarantee that the guy who's sending is still sending if a collision happened there. To do that, what they did, they came up with a nice, clever technique. They said, you know what? We will go ahead. Again, this is how, by the way, the adapter looks like. I could either be in a transmitting mode or in a receiving mode. And this is U. This is like A. And this is B. So this is transmit mode, receive mode. This is transmit mode, receive mode. You could see the cycle is the loop back here. This is how the adapter looks like. Very simple. Transmit, receive, or cycle. Very simple. We are looking at the data link layer. So how does it work? So this is what might happen. As I told you, A is sending to B. A message is going there. And then all of a sudden, I get a collision here. If I get a collision here, I need to make sure that it propagates back and A is still transmitting because A has to be in transmitting mode when the collision, when or if a collision happens. So they came and said, the IEEE said, to guarantee that A is still sending, there should be something called a minimum frame size. So we will not allow you to send anything you want. We're going to only allow a minimum size. Why? Because the time it takes you to transmit that frame should be at least the time it takes you to transmit the frame should be at least what? Definitely a bonus point. You know what? I'm in a good mood. No, I'm in a good mood. If you answer this, unmute yourself. If you answer this, I'm going to give you full grade in next week's quiz. You don't have to do next week's quiz. You
Repeat
get
the
the full
question.
grade. I'm going to repeat it. The time it takes me to transmit the frame should be at least what, in order to guarantee that if a collision happens, I'm able to hear it. Again, you need to use your microphone. Chatting, I'm not going to read the chat. I'm tired of reading chats today.
1.8 seconds.
No. I'm going to give you full grade in the coming quiz. You don't have to do the quiz next week.
The exponential that we said, or no?
No. Think about it, please.
51 microseconds.
Use logic, guys. It's not microseconds, milliseconds. No. Please think about it, please. I beg you. Use your heads.
Or can you say it again?
Yes, I can repeat the question. We're having a lot of collisions now. Okay. The question is, we said there is a problem. The problem is we need to make sure that you are still transmitting when a collision happens. Yes? We said that. We said you need to be transmitting when a collision happens. Therefore, the IEEE people came and said, okay, we have a solution. We need to guarantee that your transmission delay, the transmission time, the time it takes you to transmit your frame should be at least what? In order to guarantee that if a collision happens, you know about it.
At least you receive something?
Again, you need to use a microphone, Rafi. You need to use a microphone if you want to get the bonus point. If you don't, I'm not going to give
the period.
2T. More than 2T.
Sorry?
Twice the period.
I can. One second. Let the guy talk. The guy with the deep voice.
More than 2T? I don't exactly know how much, but slightly more so that collision.
What, can you explain? Did you Google it? Did you read it? I need explanation. I don't want a number. I want explain it to me.
No, because collision detection takes as long as 2T, right? So if the time to
why does it take 2T?
It says.
And what is T? What is T, by the way?
Period.
Time.
Basim, I'm talking to you, my friend. I want to give you a full quiz grade, but you need to explain to me, my friend. Explain to me.
Professor, can
I don't want you to get the grade as a fluke. Do you know what you're talking about, or you just guessed it, or you looked it up?
It was a guess, sir.
It's a guess. So you don't know what you're talking about. Okay, that's
no.
So,
like your honesty. So I'll give you a bonus point, Basim, but obviously I cannot give you because I don't think.
Professor.
Yeah.
Professor, who got the bonus point?
Basim.
Basim, okay.
Yeah.
Can I answer,
Okay.
Professor?
Yes, please.
I'm not quite sure about the answer though, but could it be that we compare the transmitted data with the received data?
No, we don't have data, Abdullah. We're talking about time, transmission time. Forget about data. Your transmission time is the time it takes you to transmit the message, yeah? It's called transmission delay. We did that before. It should be at least what? That was the question, and why?
Is the time supposed to be at least like 2 times the time he sends it, so that when it comes back, like there's enough time for it to come back?
2 times what? You said again?
The time that he sends it initially.
What
Like
is time?
twice.
What do you mean the time he sends it? What does that mean? What kind of time is that?
No. What I'm trying to say is there's enough time so that no matter the distance, it'll have double the time for it to come back to the.
Yeah, what is that? What do we call that, Kurav? You're almost there. What do you call that time? If you know what you're talking about, you should know the answer. If you don't know, then you do not feel good again.
Yeah, I don't know the exact term, but I kind of understood.
Do you remember the lecture I already taught you? I've taught you this before, network performance. What do we call the time for it to go and come back?
Round trip time.
Transmission delay?
No, transmission delay is a time for you to send it, my friend.
Round
What is
trip
it called?
time.
Huh?
Round trip time.
No, there's nothing called round trip time. So what is it called?
End to end?
Delay? Huh?
End to end?
No, man. Wow, you guys are not doing good today. Come on, what kind of delays do we have? We have 4 delays. I gave you a whole lecture.
Link to link delay is like overall link delay. The overall is link delay.
Okay, what are the 4 delays?
Link delay, propagation delay, transmission delay.
Okay, what kind of delay is this? This time for it to go and come back to me. It's
Propagation
2 times
delay.
what? 2 times propagation delay. Hallelujah. Deep breath. I'm gonna take painkillers today. Okay, guys, it took me half an hour just to suck it out of your, mouth. Okay, guys. Yes, as simple as this. Yes, the transmission delay should be equal 2 times what? At least 2 times propagation delay. Yes, one time. This is the one time, and this is the second time. That's what we call propagation delay. So if I could guarantee that my transmission time equal double my propagation time, I guarantee that you are still transmitting when a collision does happen. Does that make sense?
Yes, it does.
Yes, Professor.
I love this. Again, I could have clicked on the slide and gave you the answer, but if we don't think together about this, you will never remember it. And trust me now, I think you will remember it, hopefully, for the rest of your life. Okay? So yes, they came and said, to guarantee that, we need to have a minimum frame size. And they went and derived it. So I'm going to derive it for you very quick now, very easy. This is the standard of IEEE. This is the speed to find the propagation delay. We have a delay of 3.5 microsecond on each repeater. So let me just draw it for you. So we have typically 4 repeaters. So repeater 1, repeater 2, repeater 3, repeater 4. Okay? Just for you to understand the standard, how they came up with something called the minimum frame size. They said the maximum you could send is 2.5 kilometer. So this is 2.5 kilometer. Okay? And then they said we have a delay of 3.5 microsecond on each one of these guys. Okay, that's easy. And what else do we know? We know the speed is 2.3. That's the speed of the signal times 10 to the power 8 meter per second. Okay, guys? Very nice. Okay, so, and the cable length, we have it. We have the speed, and we also know it's Ethernet. So what's the speed of Ethernet, the basic Ethernet? What's the data rate of the basic Ethernet? The basic. The data rate of basic Ethernet is how much? What's the data rate of basic Ethernet? I just said it before. We have different versions of Ethernet. What's the basic one? The minimum. 10 megabit per second. 10 megabit per second. Okay, so using these numbers, we want to find the minimum frame size. What's the minimum frame size? We said, okay, it's easy. So transmission time should be equal at least double the propagation time. Okay, plus any delays we have. Of course, we have some delays here. So if I do the math, I could find now what's the minimum frame size that I need to guarantee that if I send a collision happens, I know about it. So I could do the formula for you. So the double the propagation time, you can see. So we have the numbers. So we have 2.5 kilometer divided by the speed. This is the propagation time. Okay, as you can see. And we have 4 repeaters. Each one has a delay. We multiply that. So let's do that. So we calculate the answer. We get 24.87 microsecond. This is one way. So if I multiply this by 2, I get about 50 microsecond. So my transmission time should be at least what? My transmission time should be at least
50 microseconds.
Thank you so much. And what is transmission delay? What's the formula of transmission delay? Remember? It's the size over
Bandwidth.
Bandwidth over data rate. Thank you so much, which is in this case 10 megabit per second, right?
Yes.
Is equal to 50 microseconds. Now I can easily find F, the size that I have. So let me do that for you. So I did that. So F over 10 megabit per second equals 50 microsecond. I do the calculation. Finally, we came up with the minimum frame length, which is 500 bits. Again, it has to be a power of 2, so 512 bits. And this is what I just did now, is the IEEE. This is how they derived. If you go to IEEE standard, and say, what is the minimum frame size? You would see it's written as 512 bits. And now you know why. I derived it for you. And you say, why did we do that? Just give me the number, khalas, you know. Why? Because the same logic they use, you can apply it in different networking. It doesn't have to be 10 megabit per second. What if it's 1 gigabit per second? Same thing. We can do the same derivation and find the answer. What if we're doing something else? So I want you to understand the concept behind it and not only focus on what the number is. Okay? So let me move on. So the minimum frame size is basically 512 bits. And again, this is to guarantee that if a collision happens, we know about it. Again, if a collision happens, what do? We wait. Again, we call this binary exponential backup. We wait. The first time we wait either 0 or 1. We wait maybe, let's say, to make your life easy, we wait 2 seconds. The second time a collision happens, we wait 4 seconds. The third time a collision happens, we wait 8 seconds. And again, it's exponential. We keep on going. Then it's 16. Then it's 32. So the idea here is if a collision happens again and again and again, meaning there is traffic. So don't go and send again. You will kind of collide again. So just wait until a specific amount of time and then randomly send again. This is what we call binary exponential backup. So in carrier sense, multiple access, if a collision happens, I don't immediately send. As I told you before, we do P persistent. The probability of sending decreases as we have more collisions, of course, because if I collide now and then I wait, I collide again, of course I'm going to wait more. Don't just go again because there is still traffic. So the logic says the more you collide, the more you wait, okay? And the idea is, of course, after 16 collisions back to back, you throw in the towel, meaning you stop, you don't send anymore. But typically you can see after 10 collisions, we almost wait 1024, which is 2 to the power 10 minus 1. So it's basically 2 to the power I minus 1. Every collision will make me wait more. Okay? So this is the standard of IEEE. They have a minimum frame size, and they also have a maximum. The minimum, we explained why, because we want you to be able to detect if there is a collision while you are still in what mode. You can detect the collision while you are in what mode, what state? Transmitting mode. Thank you so much. Thank you, guys. Thank you for those who are with me. Thank you. And also, we have a maximum frame length, of course. Why? Why would we put a maximum also? We have a minimum. I explained it. Why would you put a maximum? Common sense, of course.
Because there's limited number of frequency.
It's not frequency. We're not talking about frequency here because
Frame length maximum. I don't know.
Can't
I
exceed
have
the
no
limit,
idea.
it will be lost.
Okay. Sorry?
There are limits, like you can't exceed this limit. This is why there is a maximum.
Because we don't want you to have a monopoly over the channel, right? Because if I give you unlimited, you might send a 1 terabyte and we all wait there. And actually, when we send, we cannot because you're taking the channel. So that's the logic. Yes, of course. So of course, we have a maximum and then we have a minimum. And this is for the basic Ethernet, the 10 megabit per second Ethernet. So let me just finish today's lecture. So we have different networking devices that are very useful. Again, working in different layers. So we've talked about many of them, but I just want to summarize them. So you can see we have different devices. Most of you say, oh, we have a router, you know, a wireless router, the Wi-Fi that you have. By the way, Wi-Fi 802.11 works the same thing as Ethernet. Carrier sense multiple access. It has a request and a reply scenario, but it's very similar in logic to the basic Ethernet. Basically, it's called wireless Ethernet, if you think about it, okay? So different networking devices. Why do we care about different networking devices and working at different layers? Because it depends on what kind of information they decide to use, okay? For example, in the physical layer, we have the repeater and the hub, the basic, the easiest. Again, most of the, before when we have to have, you know, switches, we call them hubs and repeaters. They work at the physical layer, so they're working at the signal level. Now, the data link layer, we have bridges and switches. And of course, at the network layer, this is where it becomes expensive. We have the routers, and then we have gateways, okay? So let's talk about them equally. Let's talk about each one of them. So this is a hub connecting multiple computers together, a bridge, as you could see, connecting networks together. A switch is like a bridge, okay? So both the switch and the bridge work on the data link layer. The difference from the picture, what do you think the difference between a bridge and a switch is? Come on, from the picture, look at it. This is connecting what? Connecting what? The bridge is connecting what? Networks, 2 LANs. Thank you, Rafi. Yes. Bonus point for Rafi. It's connecting networks. The switch is connecting what? The switch is connecting what? Computers, okay? End-to-end stations. So you could see the switch is very similar to a hub, right? They look similar. The difference is, what layer does the hub work in? What layer? What layer is the hub?
The physical.
Physical. And what layer is the switch?
The data.
Exactly, exactly. And that's the difference between them. This works with frames, and this works with bits. So basically, when I'm sending here, I'm sending bits. Here, I'm sending frames. Okay? Let's go over it really quick. So repeaters. Repeaters are hub. Again, very similar. They're the simplest. They work with signals. They amplify it. If you think about it, they repeat the signal. So sometimes if you have an Ethernet cable that's not very long. So if I have if I want to put an Ethernet cable, what's the maximum distance for an Ethernet cable? I already told you. Typically around 2.5 kilometers. If I want more, what should I do? What do I use? What kind of device? If I'm working at the physical layer, what kind of device? If I want to extend the distance of an Ethernet, what do I use? Repeater. Thank you so much. Repeater, yeah? Or amplifier even, yes. Amplifier, repeater, the same. One is digital, one is analog. Amplifier is the same as repeater, but amplifier works with analog, repeater works with digital. So yes, it's very simple. It's the simplest kind of hardware, works at the physical layer, and all it does is repeats the signal. Now, if you go up, you have the data link layer. What does the data link layer do? At the data link layer, we're talking about networks now. We're talking about frames. So the bridge is very popular. The bridge connects networks together. We have 2 kinds of bridges. We have the transparent or the translating. The transparent or the translating. So the transparent LANs are basically connecting 2 LANs with the same data link, meaning they are the same. The translating is connecting LANs that have different data link protocols, making sure, again, the top layers are the same. So 2 different kind of bridges. One connecting LANs that have the same data link, meaning they understand each other. We call this transparent bridges. And one is what we call as translating bridges, okay? Which means I translate from one data link to another. So what else do we have? The router. Again, we talked about bridges and switches basically. Now, the router is working with network layer as you would expect. It's all about routing the best optimal path. That's what the router is all about, allowing us to communicate between networks over distance, over the internet, working with internet protocol and IP. Gateways works on all 7 layers. However, most popular in the top 2 layers, the application and the transport. Again, typically, as the name sounds, the gateway will allow you to go from one network, not only LAN, maybe from one MAC to another. So it's a gateway to another. So I'm working with the higher layers, typically the transport and the application layer. We already talked about hubs. And switches, as I said, they're similar to bridges. The only difference is switches work with individual computers versus bridges that work with LANs. Okay, again, they all work on different layers, which means they do the job of the layer. You have to remember, data link works with error control, flow control, error correction, error detection, medium access. All these are the job of the switch and the bridge because they work at the data link layer. Okay, so that is about it for the